All right, Pre-Cal 12, let's get after it. Here we go. We got video 21. So we are talking about logarithms. So for most of you, this will probably be your first introduction to logarithms. We're going to look at how they relate to exponents or exponentials, and then we're going to look at some of their graphs. A lot of this section here is going to be a bit theoretical, some vocabulary, and then when we get to 5.3, we're really going to dive into how we operate with them. So first thing to understand is that a logarithm is the inverse of a exponential. So you can see that if you have an exponential function, so let's just say a to the x, you would end up through means of, we're going to talk about in just a minute, solving this to here, which ends up being the inverse of your exponential. So we're going to work through the next couple of shifts, but first thing I want you to look at is this is a log, okay? Y equals log base b, okay, that's what we call the base. It's the base. And now I'm actually not 100% sure if this is real vocabulary or not, but this is what you're going to hear from me. I call x the object of the log. That's the vocab I use. And then y here is our answer. So how does a log connect to an exponential? Well, the base of the log is the base of the exponential. So that's easy enough to remember. The answer of your log is your exponential, and the object of your log is the answer of your exponential. So exactly how I switched these things around up here. See, the base of the exponential becomes the base of the log, the answer of the exponential becomes the object of the log, and then the exponent becomes the answer of the log. And the reason why we do that, the reason why we want something that can do that is because if you think about a statement where you have, like 216 equals 2 to the power of x. Well, what's x? And rather than having to work 216 all the way down to where hopefully it's a base 2 number, so say you had, base 2 to the 8 equals 2 to the x, we saw that in 5.1, then you can just say, oh yeah, x is 8. But no, what we do now is we convert that to log base 2 of 216 equals x, and then we can solve from there, which is what we dive into in 5.3. So logs and their relationship to exponentials have really good properties for where we're going to go with this. So first, let's just look at a little bit of vocab and a little bit what it means. So this is your general log notation. Okay, you got log, which stands for logarithm. N here is the base of your logs. We just call base n. And there's some restrictions on what n can be. We'll talk about that. And then a, like I said, I call the object of your log. So in that term there, that would be a base 10 log object a. Now, or sorry, a base n log. Now, if you look here, you'll notice, well, there's no base written. So if there's no base written, you just have the word log, it's a kind of an unspoken rule that it's a log 10 base. And if you look on your calculator, on most calculators, above the number 1 in orange script, if you're using a Sharp EL510, you'll see the word log there in orange. And that log is assuming base 10. So you can actually only use your calculator when you have base 10 logs. So again, in 5.3, we're going to learn how to get base 10 logs from any log expression that we have. And then again, here your object is a. Now this is just a log base 2. And then this last one's a little special. Okay, log base e. Remember, e is a proportional constant in math. It's a number that we use for many calculations, but it has a special relationship with logs. A base e log converts to what's called the natural logarithm. So it's denoted ln, which stands for natural log. A lot of people would say ln when they're reading it quickly. So people would say like, oh, ln 8 or natural log of 8. But there's no base anymore, okay, because it's just a natural log. If you have a log base e, we call it the natural log. You're going to see that a lot, so I just wanted to make sure you had an idea at this point in the video. So let's just do a bit of practice changing form. So all we're doing is we have a full statement here, so there's nothing to solve for. We're just going to change the log into an exponential. So the base of the log becomes the base of my exponential. The answer of the log is the exponent, and the object of the log is my, wow, I can't even write my numbers down right. The base of my log, there we go, and then the object of the log is my answer. And sure enough, 4 to the 1/2 means the square root of 4, and the square root of 4, 2 equals 2. Perfect. The base of my log the exponent of my exponential and the answer. And sure enough, that's 1 over 2 to the 3, which is 1 over 8. So that's just how you convert back and forth. Get comfortable doing that. You're going to do it a lot. Now, going from an exponential back to a log, well, base of my log, so log base 3, object of my log, 81, equals 4. So that's how we go the other direction. Base of my log base 3, object of my log, and solution. So again, you're going to see, because technically, yes, that's that, and you're going to see how we can convert that and prove that that is in fact true, but we will get to that again in 5.3. This is mostly going to be theory and vocab. So how do we determine a numerical solution? So in this case, just consider this, okay, log base 4 of 8 is equal to something, right? What is it? Now this is a numerical solution. This is a number. We can solve for it. In 5.3, we'll learn how to key statements in like this into our calculator, but in this one, we can actually, we're just going to convert to exponential and get a solution in that sense. So the base of my log is what? 4. So it's going to be 4 to the power of x equals 8. Now, we kind of worked a little bit on this in section 5.1. 4 and 8 are both powers of 2, so we can convert that into 2 to the 2 to the x and 2 to the 3, which now gives us 2 to the 2x equals 2 to the 3. And if you have a common base, you just have to compare the exponents. So 2x equals 3, so x equals 3 over 2. Boom. So that is the solution to that. If you plug that into a calculator in a special way that you don't know how to do yet, you would get 1.5. Then we'll do the same thing here. So let's just say, okay, log 27 of 9 is equal to x. Now I'm going to convert that to 27x equals 9. So that's the helpful part, being able to go back and forth, because 27 is 3 cubed to the x, 9 is 3 squared. So 3 to the 3x equals 3 to the 2. And again, same base. So 3x equals 2, x equals 2 over 3. So boom, solution. So we're going to learn, and we're going to work, and we're going to practice. You're going to get a little tired of logs because there's a lot going on, a lot of practice in your workbooks for this stuff. So what about the graph? Well, logarithms are the inverse of exponentials. So I just want you to look at this exponential statement, okay? F of x equals 2x. So let's calculate the inverse like we did in section 2.5. So swap the y in there, and then swap the x and the y, and then resolve for y. So in this case, this is why we have logs, right? Log base 2 to the x equals y. And wouldn't you know it, there's my log statement right there. So there's the proof that a log is the inverse of an exponential. And also you'll notice on the graph, right, our points have swapped x and y values. You could pick another point on that graph and their x and y values are going to swap as well, right? So that is how their basic behavior is of a graph, and then transformations are going to work similar. So let's look at that. So here's an example of your basic log, okay? Here you have a log of base b where b is greater than 1. So that means, you got log of 2, base 2. And now just consider converting from log form into exponential form. You get y equals, no, sorry, you don't. You get 2 equals, you get 2 to the y equals x. So just consider running this as inputting y values instead of x values. The higher you get, the longer your x value is going to get, right? So 2 to the 2, and bear in mind, this graph does not represent this equation. I just picked 2 because it's the first number that came to mind. But that is how your log is going to run. And if you just consider a basic log flipping over here, right? We had a exponential graph that would look like that. So you can see that they're going to be mirror images of one another. Here we approach 0 on the x. So for our inverse, we approach 0 on the y. And then similar here, but now we have b being a fraction. So just again, consider this as a base, and again, this base does not reflect the log you're looking at, but just consider a base of a half. Well, if we convert that into exponential form, we have 1/2 to the y equals x, but to the y equals x. But what we actually have is 2 to the negative 1 to the y. So we have 2 to the negative y. So if you compare this with this one over here, right, basically this graph here in red, what do we have? Here we have positive y values, here we have negative y values, which if you remember from transformations is a reflection of our y values, so a reflection in the x-axis. So you can see that this graph here was reflected in this graph here. So that's what a fraction to b value will do. It reflects a log just like an exponential got reflected. It's sort of direction of travel, you could say. So that's the basic log graph. Again, we'll look a little bit closer at those in the sections to come. So now let's determine the domain. Now we got some restrictions in our domain because I want you to consider just for a sec, if we converted this to an exponential, the base of my log this time is x minus 3 to the power of y equals x plus 5. Now, doesn't really help, doesn't really do much for us, but there's something to consider with respect to an exponential. If you look at, with respect to a log and an exponential, if you look at a basic exponential, again, I'm going to use 2 as an example, there are absolutely no values for x that will give me y equals 0. It's not possible, right? If x is a positive number, we get a really big number. If x is a negative number, we're going to get a really, really small number. But we're never going to get 0. And if you think about that graph of your exponential, right, your most basic exponential, you have a domain that's all real numbers, and you have a range that is y is greater than 0. So if a log is the inverse of an exponential, and the inverse domain range relationship from section 2.5 holds, that means that the domain of my log has to be x is greater than 0. So that is stipulation 1. The domain of my log has to be, so this, my log base. So base has to be greater than 0. Well, what else is necessary? If you think about the x minus 3 as the base, that x minus 3 is also going to be the base of some exponential, right? Well, there's something very simple that you're not allowed to have, and that's a base of 1. Because just imagine 1 to the power of x is always 1, no matter what it is. So if you had a base of 1, you would just have a horizontal line. So part of our domain is also then that we cannot be equal to 1 for my base. So that covers my base. But now consider, again, just for the sake of argument, instead of having all these values in, let's just say log 4, randomly pick a 4, okay, of x. Well, that gives me 4 to the power of y equals x. Are there any values of y, just like with the exponential, but with the x, are there any values of y that will give us 0? And there are not. So again, our domain, x, is still not allowed to be 0. Now we have that stipulation in our base, but we also have that stipulation in our object. Both of those, x cannot be 0. X has to be greater than 0. So it has to satisfy your base and it has to satisfy your object. And then it also has to satisfy that b cannot be 1. So we have a number of domain restrictions here. And we have to make sure that they're all satisfied. So look at our 3 domain restrictions for this. We have b has to be greater than 0. B has to not equal 1. And then x, no matter where x is in my graph, x and the x as my object, right, has to be greater than 0. So what do I get in this scenario? Well, I need this x minus 3 to be greater than 0. I also need x minus 3 to not equal 1. And then I need x plus 5 to be greater than 0. I need all of those things to occur. So in order for those things to occur, I have x is greater than 3. I have x is greater than negative 5. and I have x cannot equal 4. So if you consider this on a number line, if we have -5 here, 3 here, and 4 here, that covers this, right? But it's not good enough. We also need to cover this. And so that'll cover this. But now this chunk here covers both of these, except for the pieces of this one that don't matter. We don't actually care about any of this, because any of those values that satisfy this domain do not satisfy this domain. We need to satisfy all the domain. And then the last piece is we can't equal 4. So that means we have another gap in our domain right there. So this is all that matters. The answer to this question, the domain restrictions of this question, the x greater than -5 is redundant. It doesn't matter. We only really start counting when we get to there. So we have that restriction and we have that restriction. So both of those things happen. All right. So your base has to be satisfied with those. And whatever your object of your log is with the x in it has to satisfy that. All of those have to be satisfied. So what about the inverse? Well, show that an exponential and a log are inverses. So basically, we're not going to do the whole composite function proof, right, where g of x was actually the inverse of f of x. We are just going to determine the inverse of this. So remember from 2.5, take your function and then swap f of x for y, and then swap the x's and the y's. Now you'll notice, well, my y is kind of trapped in my exponent, and I need to solve for y, so I need to use my logarithm rules. But this plus 3 is hanging around. So let's get rid of that first. So now you have x minus 3 equals 2 to the y minus 1. Helps to put brackets around the x minus 3 to remember that it is a number in itself, because when we're doing the conversion, base of my log, and then object of my log, brackets here are very important, and then that equals y minus 1. And then we want y alone, so we're just going to add 1 to both sides. So y equals log base 2 of x minus 3, but then plus 1. So that would be the inverse. Do yourself a favor, plug that into Desmos, plug y equals x into Desmos as your diagonal line that we flipped through, and then plug that into Desmos, and you will see that they are, in fact, inverses of one another. So this video highlighted the inverse relationship between exponentials and logarithms, and we talked a little bit about the domain. We looked at some graphs, so a lot of sort of theory of logs here. In the next video, we are going to take a lot of this information, learn a whole bunch of log rules, just like we learned exponential rules, and we're going to use them to help us simplify and then eventually solve some logs. So if you're a little confused right now, it'll all make a little bit more sense as we start working with the logs in video for 5.3. Okay, thanks so much, and I'll see you next time.